Okay, let's go ahead and get started. All right, good. The lights are good to go. Today we're going to finish up our little slide on C++, namely how do we do testing, why we do testing. I'm going to go over pointers again because, again, it's very important, and hopefully that'll be the end of pointers, and hopefully everyone has a good grasp of it. And then lastly, we'll go through what I like to call the quick evolution of makefiles, which will show how we get to our final makefile that we will probably be using for the rest of our labs. After that, I'll be assigning Lab 7, which is really just what you did in Lab 6, but now we wrap it in a class. So that one shouldn't be too bad. I do add a couple of extra functions, so we'll go into that. And then I will be also assigning your first project. So we'll be getting to all that today. All right, testing. First off, who here likes to do testing? You tried.
Yeah, I mean, someone has to.
Someone has to like
Somewhere
it.
out there.
Someone.
Makes me sad.
Huh? What's that?
It makes me sad because I figure out what doesn't work, and then I can't figure out why it doesn't work.
And then doesn't. Oh. So do you like writing the test cases, or?
Sometimes, because when it runs perfectly, because like I know I want this output, and it gives me the output, I'm so happy. And then when when it runs and it gives me a totally different output, I'm like, so it didn't give me an error, but I don't know where it went wrong.
Well, at least you know then that the code is wrong, right? Mm-hmm. Right. Okay. True. So yeah, I've yet to meet a programmer that really likes to do testing. I mean, I've met some that they're okay with it, but I've yet to meet one that's gung ho. Yeah, testing. Let's do it all day. No, I never have.
It's much better than the alternative.
What's that?
It's much better than the alternative.
What's the alternative?
Not testing.
Not testing.
Watching it fail. No, I'd rather test every time. Not test.
No, not. Yeah. So unfortunately, testing is just reality. You have to do testing. Sorry, guys. I wish I wouldn't tell you that. But first off, testing will make you more productive. The earlier you find the error, the sooner you will be able to fix it. That should be at least somewhat intuitive, because the earlier you find it, the probably more fresh the code is in your mind, as opposed to if you wait 2 months and then you're like, wait, what was I doing at this point that caused this error? Yeah. So testing early on is going to help you. So I highly recommend you test as you go, as you code. Some people take it to the extreme where you should write your test cases first and then code to it. I've seen that, and that does actually work pretty well. It's called test-driven development. The nice thing is you actually are defining how you want your code to work, and then you just go and write it and make sure it works. So that's a good way to go about it if you're willing to. But you need to be testing at least. Write code, make sure you test it. Don't just send it to the autograder and hope that, I know you're going to do it anyways, but don't just send it to the autograder and hope that it works, because the autograder is not going to tell you what went wrong. But again, you do testing. This mean you will spend less time working on problems, aka data structures won't take up as much time if you test first. Right, because you're going to increase your chance of getting it right the first time, and virtually never make the same mistake twice, because if you have your tests in a suite, after you do code, you can rerun the tests. After you make a change to code, you can rerun the test suite and then not make the same mistake again, because you're testing for it. All right. The first bullet point is very, very sad. It's extremely sad. Proven fact, a computer program cannot sufficiently generate test cases for your code.
I feel like that's a challenge.
That's a challenge, good luck. Because when I say proven, I mean Alan Turing in the 1930s wrote a proof, yes, back in the 30s, that shows beyond the shadow of a doubt that it is impossible for a computer to determine if a program halts.
Oh yeah.
The program what?
Halts.
Like doesn't work.
No, not doesn't work. If I write program P, and let's say we have I write a program called halting. I send your program to halting. Halting will say whether the program halts or does not halt. That's all it says. He proved beyond a shadow of doubt that program halting cannot exist. At least with our current machines, which we haven't really evolved
Not even
from.
supercomputers.
No, they're all bounded by a certain level of complexity.
Why?
If you look at his proof, it's actually a fun one, because he said, well, what if you take the halting program and you send it to itself? So you're asking if it's going to halt the program that's going to determine whether it's going to halt. Yeah, well, what happens? Yeah, that doesn't make any sense. And he goes through actually very thoroughly. There's actually a beautiful YouTube video on this. If you really want to see it, I don't play it real fast. Sure. What's that? You like watching YouTube videos? Okay. Oh, I knew that. All right.
Once DDR5 comes out, it'll work.
If the internet works. Oh, we might be denied today. Yeah, we're going to be denied. All right, sorry guys. So the point is, if we can't even determine how it halts, whether it's going to halt or not, we much less can write test cases to determine if it halts or even gives correct output. By that I mean the program. Yes?
What is halting?
Halting, so you know how some programs go in an infinite loop? So it does not halt. Halting means that your program is just going to complete. We don't care if it what it outputs. We're just trying to determine if it completes or does not complete. AKA, does it halt, completes, halt, or does it not complete or not halt? That's all.
So, like, if you give it a program that just is an infinite loop, it doesn't know that it's an infinite loop. So
Right. Now that goes into a very philosophical question of, can a computer actually know or understand something?
I'd say seeing as there's robots with citizenship in countries, yeah, at some point.
At some point?
Roomba is kind of smart.
Yeah, so we're definitely not getting the interwebs today. Oh, here we go. I get an ad? Oh, right. We're skipping this. Well, that was not...
Ads,
Man, we,
figure out this Max Nutrition stuff.
Wow, thanks you two for betraying me. Okay.
Like the worst ad I've ever seen.
Yeah.
YouTube Red
Hey, do we get video today? I mean, sound?
or get an ad block.
I don't think we get sound. Did anyone turn the sound on?
I usually just push play.
I did. Oh, play?
Yeah.
Yes. Good call. Wow, that was amazing.
I think I did watch this.
Yeah, did you watch this in my class?
This was made in Alice.
Those movements are too smooth.
This is computing machine A. A solves problems in arithmetic.
That's nice.
It receives a problem written on paper, and it prints the answer. It always prints the right answer.
Right? Okay. Okay, doing good.
Here's another computing machine, C. C plays checkers. It receives the current state of the board, and it prints how it would move one of the red pieces. C plays checkers so well, it will never lose a game.
Terrible
First
move?
move. It's a terrible first move. You should always look at that side.
A and C are machines we can already build today, and computers keep getting smarter and smarter. So will they eventually be able to do everything? Let's feed A with a board of checkers. A was not designed to handle this kind of input, and when it tries to process it, it gets stuck. The same thing happens to C when fed with a question in arithmetic.
Like, this is the point where you move back. Now they're both.
Yeah, it's gonna explode.
Let's draw a blueprint of
As soon as they
A.
collide, it's always.
This blueprint is detailed down to the level of the logic circuits, and it fully defines how A works. We are now finally ready to introduce a marvelous machine called H. H solves what is known as the halting problem. It can analyze the blueprint of another machine and determine which inputs are good for it and which will cause it to get stuck.
You understand what it's doing?
It receives the blueprint of the machine to be tested and an input to test it with. Based on the blueprint, H simulates the given machine on the given input, and then determines if it gets stuck or not.
Right? Right. So you give the program and
H solves the halting problem perfectly. It always prints the right answer.
So if you, like, beforehand we showed that A got stuck when you fed it checkers, so this program will say it
Here
got stuck.
are 2 more examples
Okay.
with the blueprint of the checkers machine.
So it's legal input, so C's not going to get stuck. But of course, since this is still C, but we're giving an input that doesn't work for it, it's going to say not stuck. Okay? I mean, it's going to say stuck. Thank you. Thank you. It's going to say stuck.
H is a nice machine, but can we really build it?
Did you
We'll
understand
now
what that
prove
machine
that
is?
its very existence is logically impossible.
So H can't exist. Perfect. H can't exist. There we go. I'm glad you asked. It's like they stupid
Let's assume that H does exist.
All right, hold on. So, quick
We'll
little...
place it on this stand for reasons that will be made clear in a minute.
All right, so this is a proof by contradiction, which means that they're going to assume that it does exist and then show you how that is just impossible, okay?
Yeah.
And thereby showing you that H can't exist. Everyone got that? Okay. Okay, that's the type of proof this is.
Recall that we assume H solves the halting problem perfectly. It should always print the correct answer. We are about to put this to the test. This is a photocopying machine. It simply prints 2 copies of its input.
Everyone agree that program exists?
Yes.
Okay, good.
We'll place it behind H.
Oh, no. Oh, no.
Here's another simple machine. We call this one the negator. When the negator receives the words not stuck, it gets stuck. And when it receives the words stuck, it does not get stuck. And it prints a smile.
Because it's the negator.
Yeah.
Okay?
Okay.
All right.
We'll
all right.
place it in front of
Y'all
H.
believe in exists? Sure. Okay. Right. It's the negator.
Let's wrap it all in a neat package we call the X machine. X has 1 input and 1 output.
Okay.
Let's draw its blueprint. As before, this blueprint fully defines X.
I really appreciate the 2 key of that.
Okay, hold on
What
a
do you
second.
think will happen if we feed X?
Okay, hold on a second. Let me make sure y'all are clear. So we show, y'all agree P exists and N exists.
Yes.
And we're assuming H exists. So if H exists, then X must exist. Okay?
Okay.
All right? So X must be a legal machine if H exists. Okay? Is anyone not following me?
I don't understand why, like, what the point of putting.
Well, they're going to show you why in a moment. But do you agree that X must exist if H exists? That's the key thing right here. Okay. All right. So they showed you what X is, and now they're going to feed X into X.
With its own blueprint, will it get stuck? Let's find out. P simply duplicates our input. H receives 2 copies of the blueprint of X. It should now determine what happens when X is fed with its own blueprint. Let's assume it says, not stuck. N negates that and gets stuck.
Uh-oh. That's not
So feeding X with its own blueprint causes it to get stuck. But H said it wouldn't. H was wrong.
You see that?
Let's try again.
I'm so
Huh?
It's because you had it in.
Okay, well, let's do this one again. Right. Oh, yeah. No. Well, hold on.
This time, we'll assume H says, stuck.
We're assuming. I mean, no happens to be assuming.
X didn't get stuck,
All right, let's back up because I think
but H said it would. Duplicates are...
I thought it was gonna be like.
Okay, so here we go again. I'll do it again. What they're showing is X has one input and one output, and its output is one of two things, right? Either X gets stuck altogether, or it says happy face. Okay? Those are the two outputs.
Okay.
Everyone see that?
Yeah.
All right. Yes.
Why are we using a negator
Yeah.
specifically? What is?
Because it helps you understand why the halting program cannot exist. All right, so
What do you think will happen
Okay,
if
hold
we
on.
feed X?
In other words, X only has two outputs, getting stuck and happy face. Right, okay. Okay, so we're going to take, they're going to say,
With
all right,
its
so
own
those are two
blueprint.
outputs.
Will it get stuck? Let's find out.
But it puts a problem in that.
Yeah, it puts X into X. Very common
P
thing to do. in
simply
computer science.
duplicates our input.
I don't care.
H receives 2 copies of the blueprint of X. It should now.
Okay, so at this point, H is only going to produce one of two things, right? Either say stuck or not stuck, okay? So we're going to look at both of those cases, all right? We're going to look at both of those cases and show why neither of those cases can happen.
Now determine what happens when X is fed with its own blueprint. Let's assume it says
Let's say
not stuck.
which would make it a happy face as its output, right?
Right.
Because it
N
gets stuck.
negates that and gets stuck.
But then that can't happen because the negator
So
would get
feeding
stuck.
X with its
So
own
then-
blueprint causes it to get stuck.
They wouldn't negate.
But H said
So-
it wouldn't. H was wrong.
So H was wrong in that case. So it
Let's
can't
try
say that
again.
it's not stuck. So let's say maybe H puts out that it was stuck.
This
being
time,
tricky.
we'll assume H says stuck.
All right, let's see what it says. So if, then H must say that the whole thing got stuck. But if you feed stuck into the negator, it puts out happy face, which is
X
not what
didn't
H
get
said
stuck.
it would do.
Wait, so N.
But H said it would.
Do again if it gets.
H was
stuck,
wrong
it's
again.
gonna put out happy
But
face.
H is supposed to all.
If N receives the word stuck, it prints happy face. If H receives the input not stuck, it gets stuck.
I feel like you can make that now.
What?
I feel like you can make.
You can
something
make
like that.
negator, and you can make P. Yeah, both those programs exist. If both those programs exist, then this whole thing, and we assume H exists, and the whole thing must exist. Yeah.
If the negator exists and the H knows that the negator is part of the whole machine, wouldn't it know just to flip the output? It's like, oh, it's gonna say whatever I'm right is wrong, so.
Well, yeah, but it's fed that as input. Because it's fed the whole
So
machine.
why doesn't it just say, oh, print the other thing to make it right?
Because then it would be wrong. No matter what H puts out, it's going to be wrong. That's the point. Whatever H puts out, it's going to be wrong.
Why not just take out N?
Therefore, it can't
My
exist.
brain hurts.
Why not just take out N in the first place?
Well, the whole point of this is to show why H doesn't
The
exist.
negator is a stupid machine.
I like this.
Yes.
It's going to get stuck by default because like X, the blueprint of X is fed into H as both the blueprint and the input. So it's gonna do this again and then that again. Well, basically, it's gonna try to simulate the exact thing that it's doing.
Right,
And that-
which
that's-
doesn't make any sense.
Yeah. So I thought we would just get stuck because of that.
Yeah, it should get, well, yeah. But we're trying to prove that you can write a program that doesn't get stuck and always tells you if it's stuck or not stuck, which, again, we're showing can't exist, yeah.
I feel like it would get stuck with without N because if you give it its own blueprint, then P would split it, then H would it would simulate the X machine getting its blueprint, which would then simulate itself getting a blueprint infinitely. So you don't even need N to prove that it wouldn't
You
work.
do need N, because if you did not, I know what you're saying, I understand your logic, but when you write it down mathematically, if you don't put in there, and H says, I'm not gonna be stuck when I'm fed my own input, then it's correct, because it just put out not stuck, and that's what it predicted, not stuck. So the negator is there to show you why this guy up here can't work, as well as the photocopier.
But
Yes.
if
The negator is almost kind of like an error.
No, he just flips things. He's just the negator.
Is
Yeah.
it only there because it's supposed to always put the output is true to the correct output for the
Yeah,
program?
the halting program always puts out the correct
So
answer.
if it weren't always going to do that, you wouldn't need the negator because then the negator can prove it wrong.
Right, but then we wouldn't be talking about halting problem. We'd be talking about something else. Okay. If this doesn't make sense, later on, hopefully it will. But the whole point of this is that this program, this machine can't exist. Beyond the shadow of doubt. So my point is, if we can't even determine if a program halts or not, how can a computer program create all of these test cases? It can't, at least not now. So that's an advantage you have, because you can write test cases. And we can still be paid to do something and not be replaced by machines.
That too.
Real more there for a second.
Getting what?
Getting real existential there.
Sure. Anyways, back to testing. Thanks. Love that. Thank you. Oh, that was you that time? Thank you. You should like work on doing it in stereo. That'd be great. Okay. There is a lot of types of testing out there. Unit testing, what's it called? Component testing, system testing, smoke testing, user testing, blah, 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 blah. We're only going to care about unit testing in here, which is basically we take your small piece of code and we check to make sure we believe that it's working to our satisfaction. There are numerous unit tools out there. Unfortunately, there is no de facto standard for C++, unlike Java, because Java has something called JUnit, which is basically the de facto way to test Java. And that's great, because that means you only have one thing you have to worry about. Well, here, C++ is not like that. I've chosen for this class CXX TestGen, simply because, from my experience, it's been the simplest tool while still providing sufficient robustness for this class.
So this is we have to install?
Yeah, you'll have to install. So make sure to install like that. Good question. Apt install CXX TestGen. And let's go look at how a test case works. Hey, look, it's actually not that bad. So you have some clues, your function you want to test, and then you actually just create a class called myTestSuite. Make sure it inherits from CXX test, test suite. And you make a function that starts with the word test, and you can have anything after it you want. Just make sure it begins with the word test. And then it'll run it later for you. So let's go jump over to some class code. Okay, so you do the woo and he does the yay? Okay. All right, you do the claps. All right. All right, and let's do some testing. All right, let's go into testing real quick. Whoops.
I tried to install CXX code. It said unable to locate package.
Mine doesn't.
Yeah, it does that too. So I go apt.
Is it cap sensitive?
Oh yeah.
Oh, then never mind.
Wait, where are we supposed to put this?
Well, then, yeah.
In the,
Let me see if mine installs. Yep. Oh, unable to locate it. Ooh.
Yeah.
Let's go search for it then.
Yeah.
Let me see. You do a search. Oh, it doesn't exist.
I love this game.
Whoa.
CXX test. This slide is wrong. Get rid of the part GEN
wait, where do you type it? Like
in your command line.
yeah, just anywhere?
Yeah.
Okay.
Yeah. It doesn't care.
So just CXX test.
Yes.
Oh, yes, you got it.
It's doing good things.
Sudo apt install CXX test.
Install.
What?
It's a pretty decent download.
Are you sure it's not our connection? All right, let's go do first.cpp for lack of a better name. So you want to include IOStream just for printing. Let's make sure I do everything. You have to include, this is the one I always forget, CXS test. What's that? Tyler?
It says Python fly. It says additional packages inside.
Yeah, just say yes. Do you want to install the dependencies or you want to try and manually install them all?
Done already.
Oh, good. All right, what function do we want to test? Well, the slides have add, so we'll do add real quick because that's amazing.
Yes, because the slides are always right.
I know, they are always correct. Okay. And then, again, I never remember this code because I copy and paste everything. My test suite 1 public, all right. My test suite, just suite, right? Suite 1, okay. Public CXS test, okay. Test suite. And then you want to, ooh, DPW, that's kind of cool. Public void test 1. And then I'll just show you see out. I'm in test 1. Okay. Now, I wonder if that actually compiled. I mean, if that actually was typed correctly. Because you actually have to do a bunch of things. First, you have to generate the test cases. That's with the CSX test gen runner. Oh, that looks complicated. So you go CXS test gen -- runner equal, what was that? Error printer? Sure. Error printer. Okay. -o test -runner.cpp. When you run that, oh look, it didn't like it.
No input files found.
No input files found. Probably because I should say first.cpp, right? I mean, that might work. All right. What did it just do? He created this test runner.cpp. If you try and open it, you're like, well, that's a bunch of stuff that I don't know what's going on. That's because you shouldn't care about it.
Appreciate it very much.
All right. Yes.
Can we put the tester into a makefile with all of our certificates?
Oh, we're definitely going to be doing that. Hey. But I'm just going to show you the basics, and then we're going to divide it out and make nice. AKA, first make it work, then make it pretty.
Can we just skip the second part?
No.
I mean, a lot of people.
We want to have a lot of
All right, so, oh, then you just compile the program. So G++ test, and
Why
then
don't we just have a program that does this for us?
you mean make?
It's a never-ending loop.
All right, so, hey, look, I compiled it, and then I can try and a.out it. Oh, wait, I called it test runner. Hey, it passed. I'm in test is what was written. Okay, well, like someone pointed out, this is kind of frustrating. Why don't we make a makefile for it? That's exactly what we should do.
I can't do that.
So we can have a test makefile with the new font and the tester.
Oh, we can do all sorts of things, yep. So let's go put that in the makefile, and then I'll go put that in the makefile as well. I'll go open up the makefile. I'll just call it all, : let's start adding some tabs. And why don't we just run it afterwards? That sounds great. All right, make. There we go. All right. Y'all see what I did? I put it right there. Making a simple rule now. Later we'll make it pretty, but this is what we're going to stick with for now. Okay. Well, that doesn't really do much. So let's jump back to our other piece of code. I'm in test. We probably want to actually assert something. You know, like, I don't know, 1 + 1 might equal 2. Actually, I should do assert equals. Hopefully that's the case. Could be wrong. Hey, passed the test. Well, let's go and write another test. Ooh. 1 + 2 = 3. Or, ooh, that would be interesting. Uh-oh. Yep, you want to know why? Because I called the second function the same thing. Not good. Oh, see? Running test to test, okay. All right. Well, let's see what happens when we fail a test. We'll call it test 3, and we'll try and break the laws of math. 2 + 2 = 3. It's a very large 3. We'll go ahead and run. And it says, oh, you got 66% correct. You failed one of your test cases. It expected 2 + 2 = 3, but it found that 4 does not equal 3.
That's good at least.
So, yeah, this is a bad test case. We need to fix our test cases. Keep that in mind. Your test cases may be wrong. Bless you. Recompile, run it. All right, we're good now. All right. Y'all see what's going on with this code? A little bit? Okay. Then we run. Okay. Here we go. Very, very important. We want to keep our test code separate than our actual code. Okay? So currently we keep everything in a source directory. What do you think we should do with our test code? Oh, wow, amazing. Okay. All right. So let's go create a test directory. Let's go create a source directory. All right, let's go copy first over to src. We'll call it add.cpp. Let me go fix that guy up. So it now just has that piece of code. Great. And then, yeah, we'll go over here and we'll move first.cpp and we'll call it test. For this class, you are going to be happy if you end all of your test files with -test.cpp like this. And you'll see why when I go into creating a makefile that does a lot of these things for you, but we'll get to that in a moment. Okay. Okay. So let's go and update our makefile for all of this. So it's not first.cpp, it's actually called test first-test. And we also want to include our add CPP file, so that's in a separate one. And actually we don't need to include that, I lied. Because this is generating the test, so we only want to do the test. But down here, we actually want to compile the whole thing. All right. Now if I type make, multiple definitions of add first defined here. Uh-oh. Uh-oh. Oh, I know why. Probably shouldn't get it out of the test code. There we go. Nice. All right. And now they're in separate files. So we have the test in the test directory and the other code in the source directory. I'm going to go into evolutions of makefiles to make everything nice and happy and pretty momentarily. But you have any questions about how tests are set up for now? Yes?
So you did that test assert equals. Instead of doing that, would you put your function's name, or did you just call it test assert?
Right. So, right, you really want to do your function's name. You are correct. So for example, source first test. I'm surprised no one's caught me on this. Yeah, you probably want that, right? I'm just throwing that out there. So you're actually testing your code, not addition. All right, here we go. Add was not declared in the scope. Why is that? Well, we haven't included the header file for it. So let's include add.hpp. And it's going to go, what is that? Well, we probably need to define it. So let's go ahead and create add.hpp. Oh, I'm sorry. Did y'all ever learn header files? No. Okay, so hold on. Scratch what I just said. Before y'all get confused. So let's go over here, vim test first.cpp. We are going to define add. It's actually not void, it's int add, int a, int b, semicolon. Have y'all done this before? Yes. Okay, so we're going to say that this function exists somewhere. I don't know where. Make, okay. And then, if y'all saw what happened, we're saying this function is going to exist during final compilation. So go ahead and try and use it. It's going to look like this. And then, of course, if you look inside of source add.cpp, that's where we have it defined. And then if you look in our makefile, we first generate the test from just the first test.cpp, and then we compile the test runner and this add CPP file so it actually has the code for add together to then generate the test runner, then run the test. Yes?
After we do the test file, do we want to do it in the makefile where it clears this, or no?
Yeah, you can. We'll get to clean in a moment. You really just need to delete the test runner and the. Yeah, you really just need to delete test runner.cpp and test runner. That's what you need to get rid of. All right. Any other questions? Okay. Header files. Let me pause the code or